So stiffness matrix for beam element. So let us take a beam first. So what I am doing, I am considering a beam element here. Just this is a beam element. Okay. Let us take the loading condition. So what I have considered a UDL over this beam having intensity of W kilonewton per meter. So this is the UDL over a beam element whose intensity is W Newton per meter. The length of the beam is L. This is the L. Now, if you will see how many nodes we can take, we have here 2 nodes. This will be your node number 1 and this will be your node number 2, because this is the starting point, this is the ending point. So at the ends, we have to select the nodes. So there will be 2 nodes, node 1 and node 2. And the load is distributed over this beam element. If any point load will act, then we have to select the node at this point also, right? But this is distributed one, so we are selecting only node number 1 and node number 2. So now, what we are going to do, see, just I am taking the line diagram, right? So here, this is W Newton per meter. So what will be the load? WL by 2. Here, reaction. Let us take the reactional force is F1. Let us take the reactional force is here F2. The moment developed at this point, I am taking as M1. And at this point, because this is node number 1, right? And this is your node number 2. So whatever will be the at node number 1, I will give the suffix as 1, and here I will give the suffix as 2. So F2, now M2. Let us take here the moment developed is M2. Okay. Now fixed end moments. We have already discussed about this fixed end moments, or you have studied about this fixed end moments when you were studying slope deflection method or moment distribution method or Caney's method. We have discussed the term fixed end moments. So if you will see what type of loading condition is there, UDL, right? So what was the formula for fixed end moments? Fixed end moment formula was WL square upon 12. Now the second thing is on the first node, that is on the left side. So that will be minus WL square upon 12. On the second node, at node number 2, it is on the right side. So it will be plus WL square upon 12. So let us take minus W L square upon 12, and here it will be plus WL square upon 12. Okay. So if you will see this F1, so what will be the load acting at this first node? If you will divide this whole complete nodes on node number 1 and node number 2, so the total load will be W Newton per meter. So what will be the total load? So you can tell the total load will be W into L. This will be your total load, right? Newton. So now this total load is W into L. So what will be the portion of the load acting at node 1? Half of that. And because it is distributed over the length, so half of this will come here. So let us take this is WL by 2. And same half of this will go at node number 2. That will be WL by 2. So this is the free body diagram of this beam. What we have considered? We have considered the reactional forces F1, F2. Then we have moments M1 and M2. Then we have fixed end moments minus WL square by 12, because the loading condition is UDL. So for UDL, we have formula WL square upon 12, and we know on the left hand side we are taking minus, right? On the right hand side we are taking it as plus. So minus WL square upon 12 and plus 12 WL square upon 12. And if you will see this total load will be W into L, and half of the load will act at node 1 and half of the load will be taken care by node 2. So WL by 2 and WL by 2. This is the total free body diagram of the given beam element, right? Now we will take the governing differential equation for beam. Now what is this governing differential equation? You might have studied in strength of material, governing differential equation for a beam element. What is that governing differential equation? Governing differential equation for a beam, you might have come across this formula EI d to the power 4 V upon dx to the power 4 is equal to minus of W. W is the load, minus of W. Why we are taking the minus sign here? Minus sign because this load is acting downward direction, so minus W. What is V here? V is the transverse displacement. This is the displacement. V is nothing, the displacement in this beam. So if you will compare with the strength of material formula, you might have come across this formula in deflection of beams, right? In Maclay methods, integration method, you might have come across this formula. This is the differential equation governing GBE, governing differential equation for a beam, that is EI d4 V upon dx is x to the power 4 is equal to W, load, and here load is acting downward, that is why we are taking minus W. So V is nothing, where V is taken as transverse displacement, EI is bending rigidity, EI is nothing, rigidity, bending rigidity, and then W is nothing, distributed load, as we have taken in the distributed load, right? Now if we'll integrate this, let us check, this is equation number 1. Let us take, this is equation number 1. Now if you will integrate this equation number 1, what we are going to find, get, see here, if you will integrate, on integrating equation 1, this is the governing, just remember this is the governing differential equation for any beam, not only for this beam, for any beam you can apply this formula. This is the governing differential equation, right? EI d4V upon dx. Remember, this V is vertical displacement. So if you will integrate this equation number 1, what we are going to get, we will get EI. Now if you will integrate it, so what will happen, this power will decrease, right? So this will become d3. So EI d3V upon, again here this power will decrease, dx to the power 3, basic differentiation, integration, nothing is there, will be equal to minus W into x, because once you will integrate it with respect to dx, the integration of dx will be x, right? So minus W into x plus constant term, let us take that constant term as 1, and let us consider this as equation number 2. Now again, what we are going to do, we are repeating the same steps. Again we will integrate this equation number 2. Again we will integrate the equation number 2, right? What we are going to do, we have integrated equation number 1, we got the new equation, that is equation number 2. Again we will integrate the equation number 2. What we are going to get, see, once you will integrate the equation number 2, what we will get, we will get EI, the power will decrease, right? 2V upon dx square will be equal to minus W x square by 2, because that is Wx, so integration of x is nothing, x square by 2, so minus W x square by 2 plus C1, so C1 into x plus C2. This will be equation number 3. Again integrating this equation 3, what we are going to get, integrating equation number 3, again the what will happen, power will decrease, so EI dV upon dx, because here now power is 2, once we will decrease one power, it will become 1, so we can write it as dV by dx will be equal to minus W x cube by 6 plus C1 x square by 2 plus C2x plus C3. Let us take this as equation number 4. See here, again I am going to integrate this equation number 4. So what we will get here, once you will integrate it, what we will get, EI, from here we will get V because once you will integrate it, what you are going to get from here? V only. So EI into V will be equal to minus Wx to the power 4 by 24. See, here power is increasing, here power is decreasing. So this is simple integration, you should know. Plus C1 x cube by 6 plus C2 x square by 2 plus C3 x plus C4. Let us check, this is equation number 5. So we have 5 equations now. From these 5 equations only, we are going to find all the values. D square V upon dx square dV by dx means what we need here. In the previous classes, we have already discussed, we need the displacements at the node, right? So what we need the displacements. So same here, we are going to find the displacements, but the problem is, see the problem, what we have the problem. So the problem is this C1 constant term. Again, here we have C2 constant term. Again, we are having C3 constant term. Again, we are having C4 constant term. So we should know the values of C1, C2, C3, C4. Then only we will be able to find the displacement values. So from this 5 equation itself, what we are going to do? We are going to find the values of this given unknowns, given constants, right? Where I can write here where C1, C2, C3 and C4 are constants. So first step, see, till here you can consider this as step number 1. What I have done? Nothing, just I have written the governing differential equation for a given beam. Then I have just integrated it and I have reduced the power from d to the power 4 to EIV only, right? Just integrate it again and again, we will get this equation. Now what I am going to do, I am going to apply the boundary conditions. Next step is I will apply the boundary conditions. So what are the boundary conditions now? You can see here. Let us take the boundary condition. Boundary conditions. So what are the boundary conditions? So let me write. As we know, dV by dx, what we can replace this dV by dx as? We can replace it as theta. Theta is what? Slope. dV by dx is nothing, slope. So we can replace, wherever we will get dV by dx, we can replace it by theta. Again, EI d to v upon dx square is nothing. This is your moment. What moment? Bending moment. This all relation I am taking from strength of material itself. These all things you have studied in strength of material. EI d square v upon dx square is nothing, bending moment. This dv by dx, delta L, right? This is nothing, your slope. Again, we can write EI d cube v upon dx cube can be written as F. F is nothing, shear force. Everything I have taken from strength of material, these relations. dV by dx is nothing, slope. EI d2v by dx square is taken as bending moment M. EI dqv upon dx cube is taken as shear force F. Now, in boundary condition, at x is equal to 0. At x is equal to 0. What does it mean? At x is equal to 0. Let us take, this is x direction and this is your y direction, right? So since it is one dimensional element, there is no use of y direction. So only we will consider this x only, because we are considering beam element as one dimensional element. One dimensional element means the variation will be along length itself. So along the length, let us take the direction is x direction. So at x is equal to 0 means we are at node number 1. And at x is equal to L, if I am writing at x is equal to L, where we will be? We will be landing at node number 2. Because if you are moving in x direction having distance of L, we will reach at node number 2. And if you are moving in x direction with 0 intensity, then we will be at node number 1 itself. So if I am writing x is equal to 0, means I am talking about node number 1. So at node number 1, let us take the vertical displacement one, V is V1, and let us take theta value will be theta 1. Means slope at that point will be theta 1. Similarly, at x is equal to L, let us take the vertical displacement is V2, and the theta value will be become here theta 2. Okay, and we have to substitute these things in the above equation. Then what we are going to get? See, substituting these values in equation number 4 and 5. So what we are going to get? These values, we are going to substitute these values in equation number 4 and equation number 5. So what we will get? If we will substitute this in equation number 4 and 5, we are going to get EI theta 1 will be equal to C3 and EI V1 will be equal to C4. Let us take this as equation number 6. And similarly, why? Because see here, equation number 4 and 5. If you will keep x is equal to 0, because first case at x is equal to 0, v is v1 and theta is theta 1. What I said, put it in equation number 4 and 5. So x is equal to 0. So if you will put in x is equal to 0 in equation number 4, this term will be eliminated. X is equal to 0. So minus w will into 0 will be 0. This term will be eliminated. This term will be eliminated. And dv by dx. What is dv by dx? Already we have discussed. dv by dx is nothing, theta. So you can keep it here, theta. And at x is equal to 0, theta is taken as theta 1. So we will get EI theta 1 is equal to C3, because the remaining terms will become 0. Only this C3 will be left, right? Similarly, if you will keep x is equal to 0 in equation number 5, what we are going to get? If you will put x is equal to 0, this term will become 0. The second term will also become 0. The third term will also become 0. Here also x is there, so this will also become 0. Only C4 will be there. EIV will be equal to C4. And since we are talking about x is equal to 0, so V value is nothing, V1. So EI V1 will be equal to C4. That is what I have written here, right? Now coming to, if you will put x is equal to L, so what is going to happen? So we will get EI theta 2, because if I am going to keep x is equal to L, the theta will become theta 2. So EI theta 2 from this equation itself, see, will be equal to minus WL cube by 6, because see here, in place of x we have to put L, so minus WL cube by 6 plus C1 L square by 2 plus C2 L plus C3, right? So let us keep all these things here, plus C1 L square by 2 plus C2L plus EI. Now see one thing here, C3 value, here we have C3. So how we can write this C3? Because we know from equation number 6, see, already we have proved C3 is nothing, EI into theta 1. So can we write directly in place of C3 EI into theta 1? We can write it, right? Because EI theta 1 we have taken as C3. So here we have replaced this C3 by EI theta 1. Similarly, going for the next one, equation number 5, we will have EI V2 will be equal to minus WL4 by 24 plus C1 L cube by 6 plus C2 L square by 2 plus EI L theta 1, right? Because C3x, we have here C3x and C3 we know that is EI theta 1, right? So just we have replaced that EI L into theta 1. In place of x we have kept L plus EI V1, that is C4. So we have C4 value also here, C4, So we have the C4 value already we have derived. C4 is nothing, EI V1. So I have kept directly in place of C4 EI V1. So let me take this as equation number 7 and this is as equation number 8. So we got the equation for EI theta 2, EI V2, EI theta 1 and EI V1. Now solving equation number 3 and equation number 7 and 8. What we are going to get next? Solving equation number 7 and 8. What we are going to get? See. See, in this, just simple calculation, mathematics is there, nothing else. Only the thing we have to remember is that we will apply governing differential equation. That's it. Remaining everything is mathematics. Okay. So, solving the equation number 7 and 8, what we are going to get? Let us take first equation number 7. So, if you will see the equation number 7, what we have in equation number 7, we have EI theta 2 will be equal to minus WL by 6, right? Plus C1 L square by 2 plus C2L plus EI theta 1. So let us rearrange the things. If you will rearrange the thing, can we write it as same thing, C1 L square by 2, this term, I am taking this term, and C2L, this term. These two terms I am taking on one side and remaining 3 terms I am converting that into other side, because if you will see, we have only these 2 terms, in that we have unknown values of C1 and C2. These are the constant values that value we have to calculate. In this equation we have C1 and C2 again. So we have 2 equations and we have 2 unknowns. So can we find this C1 and C2? So by using the equation number 7 and 8, we are going to find C1, C2. So what I am doing, I am sending this C1 and C2 term on one side and other terms on the other side. Similarly, for equation number 8 also, I am going to do the same so that the calculation will become easy. So same thing I am going to do here. So the equation can be rewritten as C1 L square by 2 plus C2L can be written as EI theta 2 plus WLQ by 6 minus EI theta 1. Now multiplying both sides by L by 3. What I am going to do, I am going to multiply this by L by 3. Whole equation by L by 3. So what will happen? See, therefore this equation can be written as C1 L cube by 6 plus C2 L square by 3 will be equal to EI L theta 2 by 3 plus WL to the power 4 by 18 minus EI theta 1 L by 3. Let us take this equation number 9. Similarly, if we keep in equation number 8, what we are going to get? The same thing, what we have done for the equation number 7, same thing I am going to do for equation number 8. Then directly I am writing this equation number 8 after reduction. That will be written as C1 L cube by 6 plus C2 L square by 2 will be equal to EI V2 plus WL to the power 4 by 24 minus EI L theta 1 minus EI V1. Let us take this as equation number 10. What I have done for equation number 7, same I have done for equation number 8 also, and just I have rewritten this equation. That's it, nothing else. Now if you will subtract, see on the left hand side, these equations on the left hand side. To make the left hand side same, we have done these things, right? So on the left hand side, if you will subtract, what you are going to do? If you are subtracting this equation 9 and 10, so if you will subtract this, these terms will cancel out, right? So subtracting equation number 10 from 9. So if you will subtract, what is going to happen? These two terms will cancel out. C1 L to the power 3 by 6, C1 L to the power 3 by 6 cancel out. Here C2 will be outside, and L square by 3 minus L square by 2. Therefore we are going to get this as C2 L square upon 6 from here, because this sign will become minus. Similarly here also, if you will subtract, what we are going to get? We are going to get it as EI, EI V2 minus V1. V2 minus V1 minus WL to the power 4 by 72 minus 2/3 EI L, sorry, L theta 1 minus EI L theta 2 upon 3. Just subtract. You have to subtract this equation. That's it. So we will get these things. So EI V2 minus V1. Why? Because see here. EI V2 minus V1. EI I have taken outside. So this term becomes V2 minus V1, right? Because there is no V1 and V2 terms here. So that is as it is. Now we have theta 2 terms here. There is no theta 2 terms here. So it will be as it is here. Here theta 1 term is there. Here theta 1 term is there. So we have to take EI theta 1 common. So L by 3, here L. So L by 3 minus L. So 2 by 3 L. Right? And here WL square by 24. Here WL square by 18. So WL square by 18 minus, because this sign will change. This will become minus. This will become minus. This will become plus. And this will become plus. Right? So these things we have to consider. Sorry, this sign is not going to change because there is no such terms in the upper right. So just basic subtraction is there. So we have got this equation. After subtracting, we got this equation. Let us take this equation number 11, or whatever you want. Just you can take 11, because we are going to do one more thing here. Because if you will see, this is C2 here and nothing. So from here we can find the value of C2 directly. So don't take this as any equation. Directly I am going to find the C2 value from here. Then we will take this as equation number 11. Therefore, can we write this C2 value? C2 value, each and everything will be same. Only this L square by 6 will go that side, right? So C2 value we can write. See, this 6 will go up and L square will come down. So we can write 6 EI. In every term we have to multiply 6 EI upon L square into V2 minus V1. Minus here again 6 will go up, L square will come down. So L square will cancel out. This will become L square. 6 times this 72 cancels out. So it will become, after rearranging, I am writing minus here I have taken EI V2. Sorry, this will be minus. Sorry, this will be in minus itself, because if you will change the sign here, it will become minus V2 and this will become plus V2. Yes. So we have to take minus sign here also. So minus EI, 6 EI upon L square, V2 minus V1 minus 2 EI upon L into 2 theta 1 plus theta 2. Just rearranging. I am rearranging the term, minus WL square upon 12. So let us take, this is equation number 11. After just converting these terms into in terms of C2, L square by 6, I am transferring this side. From here I have taken this theta 1 and theta 2. So just 1 by 3 will be outside, right? So this will become 2 theta 1 and this will become theta 2. So minus outside, so it will become plus. So minus into minus minus, and again plus into minus minus. So everything is correct now. So we have got this C2 value. Okay, so as we have got this C2 value, so now if you will put this C2 value either in equation number 9 or in equation number 10, we are going to get this C1 value, because everything is known. Only the unknown is C1 and C2, and we know this C2 value. We have this C2 value, right? So what is unknown here? C1 or C2. So either you put it in equation number 9 or equation number 10, we are going to get C1 value. So let us write that C1 value. If you will put this C2 value in equation 9 or 10, we will get the C2 value as C1 value as C1 will be equal to 12 EI upon L cube into V1 minus V2 plus 6 EI L square into theta 1 plus theta 2 plus WL by 2. This we will get it as C1 value. Now we have C1 value, we have C2 value. Now by using these two values, we can find F1, we can find F2, we can find M1, we can find M2, and then we can find the stiffness matrix also, right? So just what I am going now, I am going to use this C1 and C2 value for finding F1 value, for finding F2 value, for finding M1 value, and for finding M2 value. So for first I am going for F1 and M1, means I am going for at node number 1. So at node number 1, if I am writing at node 1, what does it mean? At node number 1, what does it mean? X is equal to 0. At x is equal to 0, that is node number 1, and here we are going to find shear force, that is F1, and bending moment, that is M1. Already we have considered these things in the first problem, right? F1 M1 at node number 1, F2 M2 at node number 2. So we are going to find this F1 and M1. So F1 is nothing EI dqv upon dx cube. F is nothing, already I have taken this relation from strength of material, already we have discussed this. F is nothing EI dqv upon dx cube, that is shear force is equal to EI dqv upon dx cube. Now we can rewrite it as minus Wx plus C1 at x is equal to 0. Therefore, from here we can write F1 is equal to C1, because if you will put x is equal to 0 here, what is going to happen? This term will become 0. If you will put x is equal to 0, this term will become 0. So F1 will be directly equal to C1. So we have C1 value, so just write it here. Therefore, F1 value can be written as C1. C1 is 12 EI upon L cube. Already we have, this is the C1 value, right? So same value will be for F1 also, 12 EI upon L cube into V1 minus V2 plus 6 EI L square into theta 1 plus theta 2 plus WL by 2. Now similarly, now we are going to find M1 value. So let us write M1 value. M1 will be equal to EI d square V upon dx square. Bending moment is equal to EI d square V upon dx square, which will be equal to minus of, this is actually minus, right? Yeah, opposite direction, minus. So minus of Wx square upon 2 plus C1x plus C2, and at x is equal to 0. So if you will put x is equal to 0 here in this equation, what we are going to get? This term as 0 and this term also as 0. So M1 can be written as C2 minus C2, because this is here minus, so minus C2. So we can write M1 is equal to minus C2. So C2 value already we have calculated. So C2 value you can see here. C2 value is minus 6 EIL square. So just multiply it by minus, we will get M1 value. So here it will be 6 EI upon L square into V1 minus V2 plus 2 EI upon L 2 theta 1 plus theta 2 plus WL square upon 12. This is our M1 and M2 value. This is, sorry, F1, and this is our F1 value, and this is our M1 value. Similarly, same thing we are going to do, only the thing will change here at x is equal to L, right? Just we have to put at x is equal to L, we are going to get the value of F2 and we are going to get the value of M2. So similarly, if you will keep, we are going to get the values of F2 as minus 12 EI upon LQ. I am writing it directly because just what we need to do, we need to do the same thing at x is equal to L. So minus 12 EI upon L cube, V1 minus V2 minus 6 EI L square into theta 1 plus theta 2 plus WL by 2. Similarly, if you will keep, then we will get M2 also. M2 we will get M6 EI upon L square, V1 minus V2 plus 2 EI upon L, 2 theta 1 plus theta 2 minus WL square upon 12. So this is our F2 value and this is our M2 value. Now we have calculated all four values, F1, F2, M1, M2. So from this only we are going to derive this, we are going to write the stiffness matrix, because we know the stiffness matrix, the relation between a stiffness matrix and force is equal to nothing, F is equal to K into delta. So here F matrix can be written as this F matrix. How we can write this F matrix? F matrix will be written as, see, first is F1, right, at node number 1, F1 plus WL by 2. F1 plus WL by 2. What is this WL by 2? That load we have applied. The load that is W. Already we have taken the beam element, right? Here we have the load, so we have taken this is WL by 2, and we have F1 also. So F1 plus WL by 2 total force. For moment we have M1 plus fixed end moments. The fixed end moment was WL square upon 12 minus, right? So same direction, so we will add it up. Plus, I am writing here plus only. Once we will take the values, so we can write plus minus as it is given in the question, right? Just here I am taking plus, means the magnitude only. So M1 plus this fixed end moment. So fixed end moment, because this is UDL, so fixed end moment is WL square by 12. So plus WL square by 12. Similarly, at node number 2, it will be F2 plus what? Again here WL by 2. Already we have taken. So WL by 2, and for M2 it will be again here fixed end moments will be WL square upon 12. So WL square upon 12. So this will be your force matrix. Then we have a stiffness matrix into delta matrix. So what will be the delta matrix here? Delta matrix will be V1 theta 1, and at node number 2 V2 theta 2, because if you will see the shape function of a beam element, then we have four unknowns. At each node we have two unknowns. Like in bar element, we have only one unknown at one node. Means at bar element, if you'll talk, if this is a bar element, two noded bar element, so there are only two unknowns, U1, U2. But if you are talking about a beam element, two noded, so we will have four unknowns, because here we will have V1 theta 1, here we will have V2 theta 2, vertical displacement as well as rotation. Because once we are applying this load, so what will happen due to this load, the vertical displacement will happen as well as the rotation will also happen, this theta, right? So at each node there will be two displacements. But coming to this bar element, if you are applying a load like this, so what will happen? There will be no rotation. No rotation, only there will be displacement, right? Only there will be displacements, like here U1, and at this point let us take U2. So that is why here for two noded only two displacement, means at each node in bar element only one displacement, but for beam element we will have two displacements, that is vertical displacement as well as rotation. So V1 theta 1 will be at node 1, and V2 theta 2 is at node number 2. So here the stiffness matrix. Now, if this is force vector, see 4 and here displacements are 4. So what will be the size of your stiffness matrix? The size of the stiffness matrix will be 4 by 4 matrix. This size will be 4 by 4. And here it will be again V1 theta 1, V2 theta 2, and here we have V1 theta 1, V2 theta 2, and here the elements will come. That will let us take, this is K11, K12, K13, K14. This will be K21, similarly K31, K41, dot dot dot. These elements we will fill up this element. So how we are going to fill up this element? Whatever the equations we have got, see, whatever the equations we have got here for first one, for first row, what we need? F1 plus WL by 2, right? What is F1 value? See here, this is our F1 value. Now we have here V1, V2, theta 1, theta 2 plus WL by 2 is also here. So let us remove this. So what will be happen? This will go that side. So let us remove this. So what we are going to get? V1. For V1 we have 12 EI by L cube. For V2 we have 12 EI. So what is this constant value? 12 EI by L cube. So this will become a stiffness, right? Just you have to convert this into a matrix form in force and displacements. Again, we have to convert this M1 in terms of matrix form. So we will get this stiffness matrix here. We will directly convert this equation into this stiffness matrix. So if you will convert this stiffness matrix into a stiffness matrix, what we are going to get? We will get the stiffness matrix in this form. Let me write this directly, because just from here we have just convert these 4 equations into a matrix form. You will get this matrix, stiffness matrix. So the stiffness matrix directly I am writing K matrix will be given as, let us take EI by LQ as constant outside common, sorry. So first term will be 12, then we will have 6L, then minus 12, then again we will have 6L. Next will be 6L, then 4L square, then we will have minus 6L, 2L square. Then we will have minus 12, minus 6L, 12, minus 6L. Then we will have 6L, 2L square, minus 6L, and 4L square. This will be your stiffness matrix. EI by L cube is outside, 12, 6L, minus 12, 6L, 6L, 4L square, minus 6L, 2L square, minus 12, minus 6L, 12, minus 6L, and again 6L, 2L square, minus 6L, and 4L square. This is your stiffness matrix, and this stiffness matrix is nothing element stiffness matrix, because there is no global matrix here, because we have taken only one element. We have taken a beam like this having 2 nodes. If we are having 2 nodes, means only one element is there. So this is what? This is your element stiffness matrix. This is what? Element stiffness matrix. If we will have 2 elements like this, then if you will combine this K1 and K2, then we will get another K, that is called as global stiffness. Global stiffness matrix. So there is no derivation for global stiffness matrix. Based on the question, we will find the global stiffness matrix, because we know how to find the stiffness matrix for an element in beam. If we have a beam element, this will be the stiffness matrix. Directly we will calculate the stiffness, and then we can combine K1 and K2 to form a global stiffness matrix. So this is the derivation. Till here we have derived the stiffness matrix for a beam element. Suppose this one more thing is very important, because while solving the problem, while coming through this global stiffness matrix, how to combine that global stiffness matrix, let us take, we have unknowns as v1, right, displacement vector v1 theta 1, v2 theta 2, right. So this row is for v1, this is for theta 1, this is for v2, and this is for theta 2. Similarly, this columns belongs to v1, this is for v2, this is for v3, and sorry, not v2, v1 theta 1, this is v2, and this is for theta number 2. So if you want to combine two different stiffnesses matrix, so how will you combine? Suppose we have k1 and k2 like this, we have two beam elements, and for this element let us take stiffness is k1, and for this element let us take stiffness is k2, and we have to find global stiffness matrix, because if you have found k1 and k2, for analysis of this whole beam we need the global stiffness matrix. So how will you find the global stiffness matrix? Let us say here the displacement is v1 theta 1, here the displacement is v2 theta 2, and at this point let us take v3 theta 3. So how many displacements are there? We have 3 displacements, right? So this will be for, let us say k1. So what will be the value of k2? K2 value will be again something, stiffness matrix will be of 4 by 4 matrix itself, and the stiffness will be for what? Second element. It comes under these two. The second element is between node number 2 and node number 3. So what will be the unknowns here? v2 theta 2, v3 theta 3. Similarly, v2 theta 2, v3 theta 3. Now by seeing this, we have to combine the global stiffness matrix. The global stiffness matrix will be of what size? The global stiffness matrix will be of the size 6 by 6. Why 6 by 6? Because total unknown is 6 here. 1, 2, 3, 4, 5, 6. Total unknown is 6. So the global stiffness matrix will become of size 6 by 6. So what will be that? The 6 unknowns will be v1 theta 1, v2 theta 2, v3 theta 3. Similarly, here will be v1 theta 1, v2 theta 2, v3 theta 3. Now from these two individual cases, v1 into v1, what is the here? 12. Is there any v1 and v1 again? No, there is no chance of having element related to v1 and v1. So directly it will be 12. Similarly, let us take for v2, v2. I am writing for now v2 and v2. So here also, in this also v2, v2. This is the term 12, right? v2, v2. In this case also, the first element, let us take the first element is 12. So here again, v2, v2, 12 is there. So at this point, what we need to do? We need to add these two terms. So by using this concept, we will find the global stiffness matrix when coming to the problem. That is easy, nothing is there. And again, at last, we will apply the boundary condition. Don't be afraid of seeing this 6 by 6 matrix, 4 by 4 matrix. You need not to solve this 4 by 4 or 6 by 6 matrix, because once we will solve the problem, there will be some boundary conditions, and by using that boundary condition, we will reduce this 6 by 6 matrix to 2 by 2 or 3 by 3 matrix, so that our calculation will become easy. Because if at any node is fixed, then the displacement at that node will become 0. So whatever the given in the question, according to that displacement, if displacement will become 0, so the remaining, the corresponding column and the corresponding row in the stiffness matrix will become eliminated. So by using that technique, we will eliminate the rows and columns, and we will reduce the stiffness matrix, and the equation will be reduced, and we will get the unknowns, right? Okay, so we have done with that derivation, right?